All right. So I'm pretty sure we're in week 4, right? I can't believe it that we're flying. But um, how are things? How's the homework treating you? Anything we want to look at?
So I was wondering if we could take a look at number 12 on 4.1.
And I wouldn't mind 18 on 4.2.
Yeah, 18 on 4.2.
I just want to like really like I think I could got
Yeah.
it, but I just want to see it done.
And 14 and 15 on 4.2. Also.
So like all of
For
14 and
God,
2?
dude,
All right.
Yeah.
15
Yeah,
took
it's
me
just
a
like
page and a half, bro.
it's hard to tell because some of the book's answers were wrong in the past, and I think I'm doing it correctly, but
What'd you get for 15 at the end? Like
I
for
I
part
I
not for
was
part B.
totally unsure if I was doing it correctly because I was getting some weird junk. So
It was weird because we had like a
yeah,
differential equation for the first tank into the second tank.
yeah,
And
yeah.
then you had to like solve the first one, then set up the next one based off of the first
Yep.
tank influx into it.
It's very
It was
weird.
just long.
Yep, the multi-tank problems. All
Yeah.
right. Okay, well then let me go ahead and share my screen so we can go look at the homework real quick.
Cool, cool.
All right, so this is from 4.1, and it was number 12.
Yep.
So it says, suppose a substance decays at a yearly rate equal to half the square of the mass of the substance present. If we start with 50 grams of the substance, how long will it be until only 25 grams remain? So basically, we're looking for the half-life, but this is not your traditional decay, right? Because it says it's decaying at a rate equal to half the square of the mass.
Negative q squared over 2.
Okay, so let's go ahead and write that up here. So we're going to have q prime equals negative q squared over 2. So it's half the square of that remains, and then it's negative because of the fact that it's decaying, right? All right, well, let's go to the board. So here we go. We got q prime equals negative q squared over 2. So for this one, it's a separable. So we're going to get dq over q squared is equal to negative dt over 2. So that's going to give us a negative 1 over q equals negative t over 2 plus c.
Mm-hmm.
So let's multiply everything by 2. Let's flip stuff over. So we're going to get q is equal to, well, 2c, but we don't really care about that. Let me just go ahead and do the algebra here real quick. So we got minus 1 over q equals negative t plus 2c over 2. So we'll just change that to a different c. So we get q is equal to, if I change the sign on that, I'm going to get 2 over t plus c. So hopefully you got that. Does that look all right?
Mm-hmm.
Yeah, it does.
Okay.
I forgot the negative.
Well, that'll do it to you. Okay, so it says we start with 50. So that means that 50 is going to equal 2 over 0 plus c. So c is equal to 1 over 25. So we get q is equal to 2 over t plus 1 over 25. And let me get rid of that fraction inside the fraction there by multiplying by 25. So I think the equation for the amount that we have present, excuse me, is 50 over 25t plus 1,
Awesome. Thanks, Bruce.
right? And so then obviously the question is, how long do we have to go until we get to half of its amount? Well, I'll just put 25 there for Q and then solve for your T. I officially don't care enough to find that.
I got 1 over 25.
I think that looks right. So if this was, I think they said this was yearly. So 1/25 of the year. So roughly 2 weeks, plus or minus a little. All right, so how's that look? Feel all right?
Sounds good.
It was just a minus sign, Thea?
Yeah.
All right, that happens.
I must have completely spaced that it was decaying and the rate needed a negative sign.
Which will definitely change the solution a lot. All right, well, let me go ahead and share the screen again and we'll go look at the ones from 4.2. All right, so it was 14, 15, and 18.
Yes.
Okay, I was about to say, that's what I wrote down, so.
Yep.
All right, so let's look at 14 first. So for 14, we've got a 1,200-gallon tank initially containing 40 pounds of salt dissolved in 600 gallons of water. Starting at T equals 0, water that contains 1/2 pound of salt per gallon is added to the tank at a rate of 6 gallons per minute, and the resulting mixture is drained from the tank at 4 gallons per minute. Find the quantity of salt in the tank at any time prior to overflow. All right, well, let me draw the picture so that we can get all our information here. So we know that it's coming in at 6 gallons per minute. We know that it's flowing out at 4 gallons per minute. The intake has 1/2 pound per gallon. Okay, so 1/2 pound per gallon coming in, and then it's leaving out its mixture. But we know at the start, we had 600 gallons. So it was half full, since it's a 1,200-gallon tank. And the 600 gallons had 40 pounds of salt. So Q of 0 is 40. All right, so I think I got everything we need. So let's go to the board. All right. So let's get this thing set up. So Q prime, we have to look at in minus out. So how much is coming in?
6 gallons per minute.
All right.
3 gallons of
That-
salt.
That's how much water is coming
Yeah.
in.
Yeah, it's
So we
one-
need
But
salt.
at a concentration, so you'd multiply it by the concentration to get the total amount of salt going in.
Good. So we're going to get our 1/2 pound per gallon times the 6 gallons. So really we're getting 3 pounds of salt every minute. So that's what's coming in. So then what's leaving, well, again, we know we're losing 4 gallons a minute. So it's going to be something times 4. But we need the pounds per gallon. And what's the pounds per gallon going to be inside?
I had started with 4Q over the 600.
So Q over 600.
Well, yeah, start with Q over 600.
Okay, so in terms of its concentration, we know it's got Q pounds of salt. So there's our Q. But then we need to know the volume. And we can't use just 600.
So yeah, it can't just be. Well, my full was 4Q over 600 plus 6 minus 4T. And
Okay.
then
I like that. I'm just going to go ahead and
just
do
2.
6 minus 4. But our tank, we're increasing by 2 gallons every minute. So we started at 600, but then we're going to add to it 2T. So again, it's a concentration times the flow rate.
Mhm.
It's just this concentration changes with time. How long is this good? How many minutes? What's the extent on T?
Isn't it like 300?
300 minutes.
Half
So
out. It's from 0 to 300.
Right, because we have a total of 1,200 gallons, which means we can get 600 gallons more. Well, if we're getting 2 gallons per minute, that means we're good for 300 minutes. So whatever we get from this will apply 4 times from 0 to 300.
Mm-hmm.
All right, so good.
yep.
So now let's rewrite it in the form that we like. So we'll have Q prime minus, I'm going to simplify this actually. I'm going to divide all those guys by 2 in that other
2Q over
expression.
300.
I'm going to get 2Q over 300 plus T. And it's a plus now because we moved it to the other side. And that equals 3. So it is linear. It is first order. And we know exactly how to solve these.
Mm-hmm.
So we start by integrating this thing. So we're going to get e to the negative integral of 2 over 300 plus t. All right, this is going to be our, what do we call that? Y1, I think, Q1.
Q1.
Okay, so that's going to be our Q1. Excuse me.
300 plus T squared, all squared.
So it's going to be the natural log of 300 plus t times 2. The 2 is going to come in, but it's actually a negative 2. So it's going to be 1 over 300 plus t squared. So that's our Q1. And so then we get Q by doing what?
Solving the homogeneous.
This is a solution to the homogeneous. What we just found here. So what's the step after that?
Or wait.
So Brandon, you just put Q equals U times Q1.
Yeah.
But what about the C?
Well, the C is irrelevant, right?
Oh no, the C we definitely need. Because we have an initial value, right? We knew that initially there was 40 pounds of salt in the tank. So we will actually have to find our C.
So that'd be C1.
It's just going to be C. And there is no C in this finding of Q1. Because Q1, we
Oh,
just
that's
need
what I
a
meant. Okay,
solution.
okay. I thought you were talking about the C for this, and I was
Nope.
like, I thought it was arbitrary.
Yeah, and that is because we just
Okay.
need a solution. So I'm going to use the one where C is not there. Okay, so the next step, if we want to find U, we know that U prime is equal to whatever the function's equal to, so 3 over Q1. So this will be 3 times 300 plus t squared, which then we can find U by integrating that, which is just 300 plus t, that quantity cubed, plus C. And that's where the C is going to come in. So I apologize. I'm going to have to erase, but I'm going to erase our initial Q prime equals. So then what do we do with this U?
Don't you then multiply that into?
Yeah, this is now where we go to what Brennan wrote, where he
Yeah.
said Q is equal to U times Q1. Now that we've got that U, now we multiply it to this Q1. And so what we get is that Q is equal to 300 plus T plus C over 300 plus T quantity squared. Because the 1 over 300 plus T squared, when multiplied to the cube, reduces down. So Brendan, you were right. We did want to take U times Q1, but we had to get U first. All right, so any questions on Q before we move on?
Nope.
Sorry about that. I meant to mute myself before I coughed. That probably blew out your ears. All right. So now let's get our C value using the initial condition. So we know that when T is 0, we need a concentration of 40. So we're going to get 40 is equal to 300 plus C over 300 squared. So C then is going to be minus 260 times 300 squared. I don't really know what that number is off the top of my head. Let's see, 9 times 26, that 234, so negative 234,000,000, I think. I'm just going with that number, we'll see. So then Q is equal to 300 plus T minus 234,000,000 over 300 plus T quantity squared. And I think that's all they wanted, right? Was a formula
Yep.
for this as long as the T applies before it overflows. So if we wanted to find out how much we have right as we're full, we would plug in 300, and that would give us the most salt, or that would be the salt at the fullest, which probably is the greatest Q. But anyway. So better for 14.
Way better.
What were the issues with this one?
Just setting it up. It was the whole on the denominator, the outflow. It was just the 2t that I missed. So
Yeah. So if you have it so that the volume is changing, like whether it's adding or decreasing the volume, you definitely need to make sure you include that in the denominator of your concentration
yeah,
for the out.
I just wasn't sure how to include it because we really haven't encountered anything like that. I don't recall these sorts of problems enough from third quarter. No, second quarter. There we go.
Well, no, you didn't do anything like that from second quarter, but I know I showed you an example. I think the one I showed you was one that was emptying. It was flowing out more than it was flowing in. And the only thing that changes there is you would have a minus some multiple of t.
Yeah, yeah.
So, yep, they'll come. All right, so okay for 14?
Yep.
All right, let's go look at number 15. Okay, so for 15, tank 1 initially contains 50 gallons of pure water. Starting at t equals 0, water that contains 1 pound of salt per gallon is poured into T1 at a rate of 2 gallons per minute. The mixture is drained from T1 at the same rate into the second tank, which initially contained 50 gallons of pure water. Also starting at t equals 0, a mixture from another source that contains 2 pounds of salt per gallon is poured into T2 at a rate of 2 gallons per minute. The mixture is drained from T2 at a rate of 4 gallons per minute. All right, so find a differential equation for the quantity Q of salt in tank T2, and then solve that equation, and then figure out what the limit is as t goes to infinity. All right, this one we definitely need a picture because we've got multiple tanks. All right, so tank 1 has stuff coming in at 1 pound per gallon at a rate of 2 gallons per minute. So let me write that here. So 1 pound per gallon, 2 gallons per minute. So that's what's going into tank 1. And then tank 2 just says the mixture is drained from tank 1 at the same rate into the second tank T2. So 2 gallons per minute both ways. And then the second tank also has stuff coming in at 2 pounds of salt per gallon at a similar 2 gallons per minute. And then it's flowing out at 4 gallons per minute. All right, so I think I've got everything in my picture. So let's look at that. Oh, just real quick, it was 50 gallons each. And it was 50 gallons of pure. We'll just remember that. All right, so let's go to the board. All right, so here's our picture. So tank 1, 50 gallons. We're getting water in at 2 gallons per minute. That's 1 pound of salt per gallon, which then flows out into this guy. And then there's the second tank, which has that mixture from the first tank plus other stuff coming in and losing 4 gallons per minute. All right. So how are we going to figure this out?
Find the equation for the first tank.
All right. So how about we just start with the first tank? So for tank 1, we've got Q prime is equal to, well, coming in, we have 1 pound times 2 gallons per minute, so that'll be 2. And then we're losing whatever its concentration is, it's going to be Q, the amount of salt in it, divided by 50. And this one we don't have to change. We don't have to put a T or anything in there because it's coming in at 2 gallons and also going out at 2 gallons. So there's always going to be 50 gallons of water in there. So it's going to be Q over 50, but then times 2. So that'll be Q prime equals 2 minus Q over 25. All right, so there's T1. So we could easily calculate how much salt is in tank 1 by solving this one.
Yeah.
But that's not what we want, right? What we want is, what about tank number 2? Well, let's look at tank number 2. Now, I'm not going to call it Q because I want its concentration to be a different letter. So how about R? So capital R. So we're going to have R prime equals. So let's think about coming in.
So would this be dependent on both the flow in from the other pipe and the other tank? So it would be the addition of the two?
Correct.
And the inflow from the first tank would be dependent on the concentration that is currently in that tank, right?
Correct. So if we think about the second tank, we've got water coming in from the first one. And the first one, it's sending in salt at a rate of Q over 50 times 2.
Yep.
That's how much was flowing out. Remember this over here, the Q over 50 times 2? That's how much is flowing in through this one. And then we're going to add to that the 2 pounds per gallon times 2 gallons per minute.
Yep.
So there's our 2 times 2. So that's in, and then going out is going to be R over 50. Because again, we've got 4 gallons coming in, 4 gallons going out. So the concentration is always going to be R over 50 times 4. So what we actually have is what we call a system of differential equations, right? It's 2 different differential equations that involve 2 different quantities. We are nowhere near ready to try to solve those. However, we still can solve it. So what do you think we need to do?
Do we need to solve the first one and then sub that into the second one and go from there?
Yeah, that's exactly what we're going to do, because we can solve this first one for Q. If we've got that, we can plug that into the second one and then do what we need to do. So let's solve that first one for Q. So the first one, if we rewrite it, it's Q prime plus Q over 25 equals 2. So that's linear. It's first order. It's actually really nice because everything's constant in there, just good old constant coefficients. So we need a solution to the homogeneous. So it's just going to be the integral of 1 over 25, which is T over 25. So we're going to get Q1 is equal to E to the negative T over 25. So then U prime is equal to 2 over E to the minus 2 over 25. So we just need to integrate that. So U is going to equal 50 e to the t over 25 plus c. The 50 just came from like a u sub, which then means that q is going to equal the product of these. So that's going to be 50 plus c e to the minus t over 25.
Got it.
But this is an initial value problem. And we do know how much salt was in there at the start. So Ian just went like that. It's 0 because we were told it was just fresh water. So we know Q of 0 equals 0. So that means 0 equals 50 plus C. So C is minus 50. So we get that Q is equal to 50 minus 50e to the minus t over 25. So that's the concentration in tank number 1. So if we want to figure out the concentration in tank number 2,
you plug Q in.
plug that into the second differential equation. So let's see what that turns into. So for tank 2 then, we're going to have R prime equals, well, Q over 50. We can actually just divide those things by 50. And then multiplying by 2 gives me 2 minus 2e to the minus t over 25 plus 4, and then minus 2r over 25. So I just put that directly in here, the Q value, into the second. And so then rewriting that, you're going to get R prime plus 2/25 R equals 6 minus 2e to the minus t over 25, which again is linear, first order. And I think I'm going to stop this one here because you guys know where you need to go. Find a solution to your homogeneous, which is going to be e to the minus 2/25 t. Divide the 6 minus 2 e to the minus t over 25 by that value. That's u prime. Then you integrate that. Take that and multiply it by the e to the minus 2/25. That will give you another c, but we also know that R of 0 equals 0 because that tank was also fresh. Anyway, is that far enough for you guys to be able to finish it?
Yeah, no, that's totally fine.
Thank you, Bruce.
Yep,
Thank
you're
you.
welcome. And so then the second part, I guess the third part then is what happens as t goes to infinity. We'll just investigate that. You should reach a maximum amount of salt that's in that container. Like we can see that the first tank, its limiting value is going to be 50. So that one's going to get to a point where it's 50 pounds of salt in the 50 gallons. There'll be a similar number for R. What it is, I have no clue without actually doing the whole problem. I like this problem just because it shows how you can carry this forward. You know, and this was 2 tanks. I mean, what if there was a third tank and we did something similar, right? I mean, you could obviously just keep going on and on and on and on. And out there in the real world, especially if you think of this as the quote unquote pond problem, there are lots of scenarios where there are multiple bodies of water that are pouring into another one. Something that just happens to come to mind is maybe, I don't know, Lake Tahoe, which has stuff like maybe we want to look at nutrients that are coming in. So we've got water flow that's coming in full of nitrates and stuff like that from fertilizers. Well, you're going to have the bits down by the keys, and then you're going to have the part that's coming in off of Trout Creek, and then you're going to have the parts that are coming in over on the North Shore and the West Side. Right? This is a legit kind of scenario out there in the real world. Anyway. All right, good?
Yep.
All right, so let me share my screen one more time and we'll go take a look at number 18. All right, so for 18, control mechanisms allow fluid to flow into a tank at a rate proportional to the volume of fluid in the tank and to flow out at a rate proportional to V squared. All right, so the intake and outflow are both going to be varying, at least in terms of rates. So suppose that V of 0 equals V naught, and the constants of proportionality are A and B respectively. Find V of t, and then find the limit as t goes to infinity of V of t. All right, well, let me draw my picture, and then I'll share my whiteboard. Okay, so in, the rate is going to be proportional to the volume, and they said use A, so we're going to have A times V. And then out, the rate is going to be proportional to the square of the volume, and they said go ahead and use B. All right, so let's go to the board. So we got rate in, A times V, rate out, B times V squared. So we know that V prime then is going to equal AV minus BV squared. So this one's a little bit different because we're not like putting in salt or something like that. We're just changing the volume. All right, so are we good with that, Diffie Q?
Yep.
All right. So this is first order, but it is not linear because of the V squared. So what are we going to do? What technique can we use to solve this?
Can we turn it into a homogeneous?
Um,
Maybe. No,
So can
actually,
we-
never mind. Never
well,
mind.
so the homogeneous, remember we have like two ways of thinking about that. Well,
Yeah, I was thinking the
non-homogeneous.
second.
But the one is, if we set it equal to 0, well, it's not the V prime. Like we have a way of doing it with
Is it like that
non-linear.
thing that we had done?
So Brandon, what did you mean by change a variable?
Come get my cash.
Because I might guess like when you say change a variable is one of those where we go with like a U equals and try something like that.
Like, can we do the U equals PX times QY or something? I don't know. I have no clue.
Okay, so Brandon, I was correct with what you meant there. So the integrating factor, where we end up just like multiplying by a U, is always an option, right? As a kind of last ditch. But this one, we don't need to do that. In fact, you could have solved this last year in Math 106. And that should totally be the hint. Because what's the one technique that you knew how to do even back then?
Integrate.
Double integration?
So it was just integration, which means separate, right? This is a separable differential equation.
Mhm.
I can rewrite this as dv over av minus bv squared equals dt. So this guy is separable. This is probably a good time to talk about this. Let me talk to you. Okay. So at this point, we've learned so many techniques that it's really easy to kind of get lost in them. And it's really easy to try to pick the harder ones. Mostly because it feels like we're doing something, right? Like when we multiply by u, it's like, all right, we're moving, we're doing something. Don't forget about the real simple things like separation of variables. So Monty, in terms of the order you should try, for me, what I look for, first thing I look for is I look to see if it's linear or not. Because if it's linear, and we're talking, this is just first order, right? Because that's the only thing we have so far. So I first just see, is it linear or not? Because if it's linear, I know exactly what to do, right? There's that process of find your y1, then find your u, then multiply u times y1, right? So, and that's kind of what we've done the last couple. So is it linear? Yes. Okay, do linear steps. Non-linear, now I look for a couple of things. First, I look to see, is my whatever the q prime, v prime, y prime, is that equal to a function only in terms of that variable? Like in this case, it was only in terms of v. That tells me it's separable. So that's the next thing I look for, right? So think of this as a flow chart. In fact, I'm going to write out the flow chart and then we'll look at the board and I'll kind of show you what I mean. So we have linear, and then we've got nonlinear. And then once it's nonlinear, then I definitely look to see if it's separable. Because if it's separable, that's going to be easier because all I have to do is integrate and then I'm done. Okay, and then if it's not separable, then I start looking at the forms and I try to think about all the different forms that we've had. There are some like specific forms like the Bernoulli, the exact, things like that. One of my favorite things to do if I see that it's not separable, so now it's in terms of both variables, then I look to see if it's exact. That's my next go-to because that's easy. And I also know that the check for exact will also let me know if I can do an integrating factor. You know, but you also then have to keep in mind some of those other things like the u equaling y over x, right? Or so for the homogeneous nonlinear and things like that. So that's kind of my process in terms of how I figure out what I need to do. But I encourage you to sort of create your own process, something that works for you best. But that's my general thought process is I start linear or not. If it's non-linear, can I separate it? No. Now dive into the which form do I have? So that's my suggestion there. So let me show you my flow chart. So this is basically the flow chart. You just start with linear or not. Okay, if it's not separable, okay, then if it's not, look for the different forms. So I just put a bunch of boxes that didn't have names in them, but that would be like exact, homogeneous, Bernoulli, insert, 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 all the different things that we've done. All right. And when in doubt, if nothing else seems to work, try integrating factors, because that tends to bail you out in lots of situations. But better if you can recognize it of one of the forms. All right, so let's go ahead and solve this then. We're going to solve this. We have to integrate both sides. I'm going to go ahead and crack out my T89 because I don't want to actually do the integral here. If you were going to do it by hand, this would be a partial fractions problem. You'd have to factor, split it apart, do all that good stuff. But like I said, I'm too lazy for that. Okay, so we got a times v minus b times v squared. Integrate that with respect to v. All right, so I get minus 1 over a times the natural log of bv minus a over v. And that's going to equal t plus c. So yeah, Monty, integrating factors is usually my last resort unless I recognize specifically like in an exact test, you know, when you do the exact and you let your my and your nx, if like the difference of those is such that I can see immediately that it's going to give me a function of just x or y when I divide by the proper m or n. For those, if I see that, I jump right to the integrating factor that will make it exact. But for others, it's a, yeah, kind of my last resort if I don't recognize it. All right, so if we trust my TI-89, this is what we get. So if we want to go ahead and start trying to solve that for V, I'm going to get BV minus A over V equals E C times E to the minus AT. Let's go ahead and get our initial condition. We were told that at time 0, we get a volume of V naught. So that tells me that C is going to equal BV naught minus A over V naught. So whatever our initial volume is, that's what the C is going to equal. So I'll run that back up here. We now have BV minus A over V is equal to BV naught minus A over V naught times E to the minus AT. I really should have just left that as C for right now. All right, so I need to multiply by V. So I get BV minus A equals V times all this stuff. I'm going to change it back to a C for just a second, because then I need to move stuff over and factor. I'm going to get V is equal to A over B minus C e to the minus AT. And then substituting that C back in, we get that V is equal to A over B minus BV naught minus A over V naught e to the minus AT. I think. I hope my algebra is right. We'll see. All right, so that's how much is going to be in there at any given time. So I think the second part of the question said, what happens as t goes to infinity? So what's going to happen as t goes to infinity?
Is it A over B?
Yep. So if we take the limit as t goes to infinity of this, the part with the e is going to go away
Yeah.
because we get e to a really big negative number that's going to go to 0. And so what this is saying is the amount of water we're going to have in there is going to equal the ratio of those two constants. So A over B. Don't ask me about a real life situation where this would happen, but at least in the minds of a math textbook writer, it's a serious, significant application of differential equations.
It's like those math problems where like someone goes to the store and buys like 50 watermelons.
Sure.
Yeah.
I
Like
have no idea what you're talking about, Wes, but sure. Because nobody ever buys 50 watermelons.
Yeah, yeah, exactly.
Unless you're having a really, really big picnic barbecue or something.
Yeah.
Making a lot of jungle juice.
Yeah, right. All right. So, okay for number 18?
Way better. Thank you.
You're
Yeah,
welcome.
thanks. I appreciate it.
So just notice how I attack these problems. Right? I always start with create the differential equation. And specifically for these pond problems, I do in minus out. I just look at how are these things changing with stuff coming in versus going out. And then once I've got that, then it's a matter of figuring out what form it is and doing the right steps to get the solution. So anyway. All right, so there's a little bit more about the mixture problems. And so what I want to do with the rest of today is talk a little bit more of the mechanics and actually take drag into account. So I already kind of gave you the preview of where this was heading, but let's actually do it now. Let's move past the physics of ignore air resistance to let's have drag and see what occurs. All right, so let me go back to the board and real quick remind you what I'm talking about. So what I showed you last time was that we can actually solve a mechanics problem by finding velocity if it's set up the right way, right? So Newton's good old second law is that F is equal to ma. And we saw that if we can write that force as a function of only t and the velocity of time and velocity, then this is something that we can solve because A is actually equal to F prime, or V prime, I mean. So if we're in a situation where the force is only dependent upon how much time has gone by and how fast it's moving, then you're good to go. What we can't have is something that depends on position. Because if it depends on position as well, this is now a second order differential equation and we're not ready for that. But soon we will be. So we're going to allow for those things in not too long. And that will really open up what we can do. So as long as the force is only dependent upon time and speed, we have the techniques to solve it. All right, so let me show you how this is going to work and how we can deal with drag. Okay. So for example, let's just say that we've got a falling object and that it experiences drag at a rate that's proportional to its speed. Which makes sense. That the faster we're going, the more drag we're going to have. So this is not a bad assumption. It's not always a good assumption, but it's better assumption than no air resistance whatsoever. So let's think about what this is going to look like on a free body diagram for this object falling. So in terms of the forces, as you know, we always put gravity. I love when I teach physics, and Ian can back me up on this. At any time we're talking about force diagrams, the very first thing anybody mentions is gravity, and it's always Victor. I think Victor's just ready. I think he's like got a hotkey on his computer or something. He just types G and it goes gravity.
Gravity and normal, gravity normal, gravity
Yep,
normal.
gravity normal. So we've got gravity pulling it down. And when you first took physics, this was it. Object falling, this is the only force. But now we're also going to have drag. And so that drag, it's actually going to be opposing motion. So in this picture, it's pointing up. So an object that's falling, the drag, the wind resistance is going to be pointing up because it's trying to slow it down. So we can actually put this all together. And what we know then is that the total force is going to be gravity minus drag. I'm going to make it so that plus is down. I know that might feel a little bit weird, but I like to make my plus in the direction that I'm traveling. So we're going to let force equal gravity minus drag. So that force, that's going to be mass times its acceleration, so m times v prime. Gravity, gravitational acceleration is mass times gravity, right? The acceleration is g, so the force is actually m times g. And then the drag, okay, well, I told you it's at a rate proportional to its speed. So let's just make it some k times v. And so what you will see is they call this k, or whatever letter they use, the drag coefficient. Depending on the book, they'll use different letters. A really common letter is gamma, actually. We use gamma a lot for that, but that's going to be our drag coefficient. Well, this is linear. This is first order. So we can go ahead and solve it. So how about we do this? How about we just solve it with all the letters? Do it the math way of let's solve it once, and then we've got our answer for every single one of these ever. So I'm going to rewrite it. I'm going to divide by m, move some stuff around. So I'm going to get v prime plus k over m times v is equal to g. So it's linear first order, which means we can get our v1. It's going to be e to the minus k over mt. I don't know if you guys have spotted that pattern yet, but if it's ever a constant times v, it's
You
always
just
e
tack
to
on
the
the T. Yeah.
yeah, it's always e to the negative of that times t. So there's our v1. So then we know that u prime is equal to g over that. So if we take that minus and bring it up top, and then we integrate that, we get u, it's equal to gm over k times e to the k over mt plus c. So now we just need to multiply that by the v1, and we get v is equal to gm over k plus c e to the minus k over m times t. So you guys should all be excited about this for a couple of reasons. First, we're not ignoring air resistance. Yay. This is much more applicable. And secondly, you should like this because we now have the solution to every single one of them. The only things that are going to change are the mass of the object and the drag coefficient. And that drag coefficient is going to depend upon the object itself, right? Certain things are going to experience more drag than others, depending upon their smoothness, their design, their aerodynamics, whatever.
So like stuff that could affect the drag coefficient would be like the surface area of the object,
Yep.
The texture of the object, I guess, would also be a factor.
Yep.
Just in general, what shape it is, because certain things could just go through rather plummet faster than others. So.
Yep. Yeah, those are definitely things that matter. Other things that matter would be the material that it's falling through, right?
Picture.
I didn't say, like when I drew this picture, were we falling through air? Were we falling through water? Were we falling through honey? Right? I didn't say at all what the fluid was.
So it could also matter on the viscosity of whatever material that you're following through.
Exactly. Yeah, the properties of the fluid will affect that drag coefficient. So another interesting thing while we're talking about it, like if, let's say this was in a fluid, there's another force I need.
Oh, the buoyant force.
Yeah, the buoyant force. And technically, we would need that even in air, but the buoyant force of air is pretty small. If you guys don't remember, the buoyant force, it's dependent upon the mass of the fluid that gets displaced. And obviously the mass of air is pretty light.
Yeah.
It's pretty small, so you don't end up getting much of a buoyant force. However, technically we would need that as well.
So if you were to be, just as a thought experiment, if you were to be falling through like a denser atmosphere, some gas that's a little bit more dense than just air is, that would affect the generally how everything goes about with falling, essentially.
Yeah, it's going to change that K. Let's just look at this formula for a second.
Mm-hmm.
So we've got this GM over K. Okay, that is what it is. But, well, actually, what is that? Check this out. What happens as T goes to infinity? What happens to that E part?
Doesn't that just, let's hear, it just goes to C then, right? Or,
Well, T goes to infinity. There's going to be E to the minus infinity, which is 0.
yeah. Okay, so
this whole C piece goes away.
Drops out.
So what this tells us is that there's a maximum velocity. If we look at the limit as T goes to infinity of V, it's going to equal GM over K. And this is what we call terminal velocity. So if you've ever heard that phrase, terminal velocity is the fastest speed that a falling object is going to take. And the reason is, as we fall faster, drag increases because it's proportional to our speed. So eventually we're going to be going so fast that drag balances out gravity. And now we're in equilibrium of forces, so there's no acceleration. All right, so just check this out. So G is because of Earth. Obviously, we might be on a different planet or something, you would adjust that. But that's just because we're on the Earth. So the more massive an object is, the greater its terminal velocity will be. But also the smaller K. So smaller K means you can get faster speed. So K, the bigger K is, the more drag you experience, the thicker the fluid is. And so it slows you down more. So to your point, Theo, when you were saying, well, what if we were, you know, in an atmosphere that was thicker or something like that, then yeah, we'd have a greater K, which means we wouldn't reach as high of a speed because it's pushing us back more.
Yeah.
And then you can also see how those things affect this piece, because this e to the minus kmt, we're adding that, it's going away exponentially, but the k over m tells you how quickly that goes away. And so the bigger k over m is, the faster that goes away.
Got it.
So a lighter object will reach its terminal velocity faster. Or another way of thinking about it is if you're in a denser fluid, a greater K, if there's more drag, then you not slow down, you reach that terminal velocity in a quicker manner. So the beauty of this is that we've done this for any kind of atmosphere, any kind of fluid, if we ignore buoyancy. Throwing in buoyancy doesn't really change much. I mean, it will change what the solution looks like, but the process is pretty much the same. All right, so there you go. You now can handle anything that's falling. So for example, let's just do one real quick. We're gonna go ahead and be on Earth, and let's say we've got a 10 kilogram mass falling. And we're going to fall from rest. Okay, but what we know is that the drag coefficient, actually, I'm not going to give you the drag coefficient. I'm going to tell you that it experiences I just want to see if I can get the numbers to be exactly what I want. Let's just say it experiences 10 newtons of drag when traveling 2 meters per second, not 5 meters per second. So let's see if we can find the equation for its position. So I'm going to leave this box here because I want to use that. See, we've got the solution for everything. But let's start putting in what we know. So we've got a 10 kilogram mass. So we've got m is equal to 10. G, since we're on Earth, that's going to be 9.8 meters per second squared. So the other thing we need then is K. But notice I didn't give you the drag coefficient. So how are we going to calculate it? That was like the perfect response.
there are a lot of factors that go into that.
Well, it's this line right here.
Oh, got it.
10 newtons of drag when traveling 5 meters per second. You know that the drag force, that's proportional to the velocity. That's how we, like when we derive this, that's what we assume. So that tells us we've got 10 newtons is equal to K times 5 meters per second. So we can just do that division and get that K is equal to 2. And the units on that are kilograms per second. So if you know a drag force for any speed, that's going to be enough for us to find K. All right, well, now let's just put everything in. So we're going to take 10 times 9.8, that's 98, divided by 2 is 49. So we get k is equal to 49 plus CE to the minus 1/5 t. That's our k over m. And then the last thing is we knew we were falling from rest. So falling from rest tells me that v of 0 equals 0. So that gives us 0 equals 49 plus c. So c is minus 49. So we've got v equals 49 minus 49e to the minus 1/5 t. So there you go. There's the velocity of that 10 kilogram object that's subject to the specific drag. But we haven't actually answered the question I asked. Because what did I ask us to do? So find k we actually did along the way, Brennan.
Find the equation,
equation for
its
position.
position.
We want position. This is just velocity. So we got to do one more step, and that step is to integrate.
Integrate.
So if we want position, let's just call it y. Y then is going to be the integral of v with respect to t. That's going to be 49t plus 245 e to the minus 1/5 t plus some arbitrary constant. And what's this arbitrary constant going to be?
Is that going to be its initial position? Right? Yeah.
It's its initial position, or, well, it's related
Mhm.
to its initial position, right? In order to find that, we'd have to know where it was. So like, let's just say that y of 0 was h for its height above the ground. Then we get h is equal to 245 plus c. So c is h minus 245.
So this is just sort of a more advanced version of the original position equation that we derived back in early Math 106.
Exactly.
Because I can see portions of it that sort of stick through that remind me of certain sections of the traditional position equation.
Yep.
Like you have your where your initial position affects the overall position of it, after how long that 49t is affecting, like it's essentially just the velocity, your initial velocity of it, that gets sped up over time.
Yep.
It's interesting.
Yeah, and you're exactly right, Thea. If you go back and you look at how we built that, we were saying that the only acceleration was gravity. Now we're throwing in another force, the drag force. So what we got with gravity should still show up, right? I mean, that should still be kind of playing part of the role, which it does. But it's definitely more complicated because of the fact that we are now incorporating drag. But yeah, it's the same process. And you think about how we ended up getting two constants of integration, one that came from the initial velocity and one that came from position. That's what happened before. That's still what happened, right? We got this first c that was dependent upon our initial velocity, and then the second c was dependent upon our initial position. So yeah, we're not reinventing the wheel. We're just using different forces. All right, well, there you go. You now have every single one of these problems solved. It's just a matter of plugging in the correct respective pieces.
However,
and you know there's always the yeah but, right, the other shoe, is it's not always that drag is proportional to velocity. Sometimes it's proportional to the square of the velocity or the square root of the velocity or something else, depending upon, and that's kind of what Thea hit on earlier, was like the drag of the specific object. A specific object, because of how it is constructed, its shape and all that, may not always be found to have a drag coefficient that's proportional to speed. And I just want to show you what happens if we make it so that it's proportional to the square of the speed, for example, how quickly that changes what the structure of the position function looks like. Okay, so this one, let's do it this way. Instead of being proportional to the speed, let's make it that drag is proportional to the square of the speed.
So basically, this just means that as it speeds up, it experiences drag faster. Okay, so like when you double the speed, you're actually quadrupling the drag coefficient. Well, let's just do it generically, kind of like we did before, and see what spills out. So now what we're going to get is that our force, so our mv prime, our ma, we're still going to have gravity pulling us down, but now we're going to have a drag that's proportional to v squared. So if we were to do the same thing as before, we're now going to have v prime is equal to g minus k over mv squared. And so this is no longer linear. So let's go back to the how do we figure out what technique to use? All right, so this kind of goes to Monty's question a while ago. So first thing I notice, remember my check is it linear or nonlinear? I see the v squared, okay, nonlinear. So then what is it that I said I look for next? If it's nonlinear, what's my first hope?
Separable.
It's separable. Yeah, so is this separable?
Yes.
Absolutely, right? V prime is a function of V only, so I can separate this. So that's what I'm going to do. I'm going to get M over mg minus kv squared times dv is equal to dt. This is what you get if you get a common denominator, and then you have to divide by it to separate. Now, I want to mention this before we go too much further, because this is something that's a little bit different than we saw with the other one. When it was just proportional to the speed, we didn't have to worry about if it was going up or down. Because up or down, the only difference was we either subtracted or added that linear piece, which didn't change how we integrate it. But this one, depending upon which way we're going, absolutely matters. Because what I've got for this setup, this is set up so that my object is falling, right? It's going down so that the drag is pointing in the opposite direction. If I was going up, my drag would now be pointing down, which would make this a plus because it needs to point in the same direction as gravity. And notice why it matters. What's the difference between, as I have it written here, with a minus and a plus when it comes to integrating?
Wouldn't that affect your U sub at the end as you're integrating? Wouldn't it flip the sign basically?
Not just flip the sign. Like, what if that's a plus? What do you get when you have something of the form like 1 plus x squared on the bottom?
Oh, that's arctangent.
Yep. So if it's
Oh.
a plus, we're going to get inverse tangent. If it's a minus, then you can use partial fractions, split it apart, and you'll have natural logs. So you're going to get a completely different looking solution if it's positive or negative. You're either going to get something that's an E or something that's a tangent. I'll show you. I'll show you what happens when we throw it upward. But for right now, just recognize that it definitely matters. Right. So at this point, I'm actually going to stop because of the fact that it does two different things, and I don't want to go through the whole process for both. But notice that it's kind of the same idea. Now that we're here, we just integrate, and then we can solve for V, and we're good to go. Before I actually do an example, though, I want to show you another way that we can find terminal velocity that doesn't require us to actually get the equation for V and then take a limit. Like that's what we did last time, right? To find that GM over K stuff. Let me show you another way to find terminal velocity. All right, so to find terminal velocity, what we know is that at that point, V prime is equal to 0. Because we're not changing our velocity anymore. We're not speeding up. We've reached our maximum speed. So what we can do is actually go back to the very beginning equation and put 0 in there for V prime. So we would get 0 equals mg minus kv squared. So v squared is going to equal mg over k. So then v will be the square root of mg over k. So it's exactly the same idea. It looks a little bit different now. If you go back and you look at what we found for the other one, what was the formula for the terminal velocity for the linearly dependent on velocity? Well, it was just mg over k. It was the same stuff in the square root, but no square root. So it shouldn't surprise you that they're actually related to each other. But this one is actually going to be the square root of the terminal velocity otherwise. But this is kind of nice. We didn't actually have to go through the process to calculate our velocity. All right, well, let me show you an example. And specifically, let's look at one that's going upward. So this is going to be, I'm going to take my object and I'm going to toss it up. So think about what's going to happen now in terms of drag. So since we're throwing this upward, gravity is still pointing down, but now drag is also pointing down. So in the context of this problem, now instead of having the minus kv squared, we're going to have the plus kv squared. So our mass times v prime is going to equal mass times gravity plus kv squared. So again, I'm just making it that down is positive. All right, well, let me give you some specific numbers. Let's take that same 10 kilogram object. But let's just change it so that I'm just going to give you a drag coefficient. And this time, let's just say that k is equal to 1, just to make life easy for us. So here's what this is going to look like then. We're going to have 10 v prime equals 98 plus v squared, which is separable. So if I separate this, I get 10 over 98 plus v squared. That's going to our dv is going to equal dt. So this is going to give me an inverse tangent. I have to do a little bit of algebra to it. I have to divide by 98 to get 1 plus. Then I have to do the u sub where u is equal to v over the square root of 98 and blah, 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 blah. But what we end up getting is 5 root 2 over 7 times the inverse tangent. And it's the inverse tangent of root 2 over 14 times v. So that's going to be this. And then that's going to equal t plus c. So this is another initial value problem that if we knew what c was, we could go ahead and calculate that. No, if we knew the initial velocity, I should say. But even without, we can go ahead and solve this. And what you end up with is that v is equal to 7 root 2 times the tangent of 7 root 2 over 10 times t plus c. It's a different c, but it's still an arbitrary c. But remember that this is only applying while we're tossing it, while it's going upward. Because once it reaches the top and starts to fall, that changes this original differential equation to a minus kv squared, which leads to a different solution. So think about that. If we want to talk about its position, we're going to get a piecewise defined position function. There's going to be the function that's describing its position as we go up, and then we have to switch to the other one as we come down. Hopefully, this discussion today has shown you why, when you take Physics 107, we say, ignore air resistance. Because imagine if this is how we started you in physics. You'd probably be
It'd
like,
be very
oh,
overwhelming.
yeah,
and
you'd say, screw this. I don't want to do any of this anymore. And you would never get to a point where you even learned anything about energy or anything like that.
any of the cool stuff.
Yes, the cool stuff and the important stuff, right? And that's why we give you the, well, let's just set the ground. Let's set the table with the basics. And then once you're comfortable with the ideas of forces and acceleration and energies and all that, then let's up it. Let's go to the forces that are not constant. And let's go to where we have drag and all that. I mean, not only was your math level not quite ready for it, I mean, technically, yeah, you could have done these since they're separable. Your math level was there, but it would have been totally overwhelming and you guys would have all dropped and there'd be like 2 people in second year physics.
It's sort of like the whole, oh, technically you don't need calculus for linear algebra, but it's good to have some more advanced math behind you to like help you get used to everything.
Yep, absolutely. And just like, you don't necessarily have had to have taken linear algebra in here, but I've already referenced it.
Yeah.
Right. And so it's just like anything, you get a little bit of, if you get that background first, then it makes it easier if you want to build on it. And
yeah.
Then you can even start bringing things together from different fields.
Like, I mean, with linear algebra, at least from what I've experienced, like with some of these differential equation proofs, it makes it very easy just to do like a simple like 3-line proof. using linear algebra for differential equations because of the derivative is a linear operator, you know.
Yep, that's exactly true. So if you see those connections, it can be really, really beneficial, but not necessary, right?
Yeah.
You don't have to have it.
You don't have to, but it's very nice to recognize it where it is, you know.
For sure. Okay, well, I think I'm going to stop here. In terms of where we are, you remember how we were ahead of schedule? Yeah. Not anymore. Today we definitely slowed down a bit, but that's okay. I don't mind because I, especially when it comes to talking applications, I'd like you to see them and get a better feel. So we're still kind of in the middle of 4.3. So I know that with homeworks and stuff, 4.3 now all of a sudden is due on Wednesday and we haven't even finished it all. So I think what I'm going to do, I'm going to move 4.2 to Wednesday. So if you're not quite done with that, you got a couple more days. If you're already done, don't get mad. Just think of it as, okay, you've got a couple days of not having to do it, right? And you can go ahead and start into 4.3. You'll probably be able to do quite a few of them. But I want to talk about escape velocity, which is another thing that comes up in physics that requires some differential equations. So we'll address that at the start on Wednesday, and then we'll figure out where we're going to go from there. I think I might cut out section 4.4. If I end up deciding to do that, I will let you guys know. So don't start working on the 4.4 homework. I don't think anybody would, but obviously I'm going to change the dates on those as well, the 4.3 and 4.4. But we still are going to have our exam on Friday.
Yeah.
So, and what did I tell you that was going to, did I say chapter 4 was going to be on that?
I believe no, or
well, I'll tell you what. I tell you what. We're going to make it so that the stuff from 4.3, the mechanics stuff, is not on there. Okay. So no matter what I told you before, now it's just going to go through 4.2. So through mixture problems.
Got it.
So you'll get the differential equations applications that we've talked about. You know, so you know, exponential growth, radioactive decay, the financial stuff, like that kind of thing, and mixture problems, but that'll be it. Okay, so
cool.
All the techniques and then applications up through and including mixtures. So my guess is that probably what we'll do on Wednesday is I'll show you escape velocities, and then we'll probably spend the rest of the time kind of reviewing for the test. So
cool.
Anyway, so that's where we are. I'm going to go ahead and pause the recording here.